Imagine you were driving on this road and then you see this crack. Now you have to take a 5 miles detour to avoid the crack. If you were driving in the Midwest of the US, the breaking in the road is probably due to clay swelling, because the Midwest has a lot of clay deposits in the subgrade of the soil. The traditional geotechnical approach to solve this problem is the addition of lime and water to it to make clay stronger. But the internal chemical processes that makes clay stronger and it solves this problem is not known to us. So we can use the state-of-the-art molecular tools to explain this behavior. As you can imagine, the road breaking due to clay swelling has economic consequences, and it has been reported that it costs $1 billion annually. So the treatment process is addition of clay and water and lime to make concrete soil. The research questions are how the chemistry of clay and lime help make this process happen. The approach we are taking is we are creating a lab replica of the real life situation. We are taking pure clay minerals. As you can imagine, there are various clay minerals in nature, and we are taking the extreme left and extreme right clays in the clay risk continuum. The one on the extreme left is kaolinite, which has low swelling potential, and the one to the extreme right is bentonite, which has higher swelling potential. And the approach is we add lime and water to the clay and let it cure for some time, 7 days, 28 days, 90 days, up to, I am curing my samples up to 2 years. When the cure time is over, I'll take the clay, do the strength test on it, which is the microscopy analysis. And for microscopy, I would use state-of-the-art spectroscopy techniques like NMR, which is very similar to MRI that doctors do to see what's happening inside your body. And then from my preliminary results, as we can see, the microscopy point of view, for bentonite, the clay with high swelling potential, it is gaining strength very quickly in 28 days. The industrial standard right now is 28 days for curing days for clay. So I guess we can continue that for bentonite, but for kaolinite, the strength is still increasing. And from the molecular point of view, as we can see for bentonite, the amount of free lime that is available for reaction drops very quickly, and then it kind of flatlines. For kaolinite, it is dropping down, the amount of free lime is dropping down at a very slow pace. So the end goal is we will take all this data together and put it in a kinetic model that can predict the behavior of clay, and hopefully you won't have to suffer from unfortunate clay swelling in the roads anymore.